Assalamualaikum and hi everyone. My name is Nabila binti Abdul Khalid. Now I will present about the heat transfer, the modes of heat transfer, which is the radiation. First of all, consider a hot object that is suspended in an evacuated chamber whose walls are at a room temperature. The hot object will eventually cool down and reach thermal equilibrium with its surroundings. That is, it will lose heat until its temperature reaches the temperature of the walls of the chamber. Heat transfer between the object and the chamber could not have taken place by conduction or convection because these two mechanisms cannot occur in a vacuum. Therefore, heat transfer must have occurred through another mechanism that involved the emission of the internal energy of the object. This mechanism is radiation. For the figure 2, we will recall the heat transfer by conduction or convection takes place in the direction of decreasing temperature, that is, from a high temperature medium to a lower temperature one. It is interesting that radiation heat transfer can occur between two bodies separated by a medium colder than both bodies. For example, solar radiation reaches the surface of the Earth after passing through cold air layers at high altitudes. Also, the radiation absorbing surfaces inside a greenhouse reach high temperatures even when its plastic or glass cover remains relatively cool. Accelerated charges or changing electric currents give rise to electric and magnetic fields. These rapidly moving fields are called electromagnetic wave or electromagnetic radiation, and they represent the energy emitted by matter as a result of the changes in the electronic configuration of the atoms or molecules. Electromagnetic waves are characterized by their frequency and the wavelength. These two properties in a medium are related by the equation of 11.1. It has proven useful to view electromagnetic radiation as the propagation of a collection of discrete packets of energy called photons. Each photon of frequency is considered to have an energy of, as shown in the equation of 11.2. A black body is defined as a perfect emitter and absorber of radiation. A black body emits radiation energy uniformly in all directions per unit area, normal to the direction of emission. The radiation energy emitted by a black body per unit time and per unit surface area can be expressed as in equation 11.3. Sometimes we need to know the spectral black body emissive power, which is the amount of radiation energy emitted by a black body at an absolute temperature T per unit time, per unit surface area, and per unit wavelength about the wavelength. The relation for spectral black body emissive power known as Planck's law, can be expressed as equation 11.4. The integration of the spectral blackbody emissive power over the entire wavelength gives the total emissive power as shown in the equation 11.6. The ratio of the radiation emitted by the surface at a given temperature to the radiation emitted by a black body at the same temperature is between between 0 to 1. The emissivity of a surface represents the ratio of the radiation emitted by the surface at a given temperature to the radiation emitted by a black body at the same temperature. It varies between 0 and 1. Emissivity is a measure of how closely a surface approximates a black body, for which emissivity equals to 1. Spectral directional emissivity, which is defined as the ratio of the intensity of radiation emitted by the surface at specified wavelength in a specific direction to the intensity of radiation emitted by a black body at the same temperature at the same wavelength, that is in equation 11t. The directional emissivity is defined in a like manner by using total intensities, or the intensities integrated over all wavelength, as in the equation of 1131. In practice, it is usually more convenient to work with radiation properties average over all directions, called hemispherical properties, noting that the integral of the rate of radiation energy emitted at a specific wavelength per unit surface area over the entire hemisphere is spectral emissive power. The spectral hemispherical emissivity can be expressed as in equation 1132. Finally, the total hemispherical emissivity is defined in terms of radiation energy emitted over all wavelengths in all directions, as in equation 1133. Therefore, the total hemispherical emissivity, or simply the average emissivity of a surface at a given temperature, represents the ratio of the total radiation energy emitted by the surface to the radiation emitted by a black body of the same surface area at the same temperature. The total hemispherical emissivity can also be expressed as in equation 1134. To perform this integration, we need to know the variation of spectral emissivity with wavelength at specified temperature. Now we go to the example. The spectral emissivity function of an opaque surface at 800 Kelvin is approximate as in figure 1130. Now we need to determine the average emissivity of the surface and its emissive power. The variation of emissivity of a surface at a specified temperature with wavelength is given. The average emissivity of the surface and its emissive power are to be determined. The variation of the emissivity of the surface with wavelength is given as a step function, as in figure 1130. Therefore, the average emissivity of the surface can be determined from equation 1134 by breaking the integral into three parts, where f lambda 1 and f lambda 2 are blackbody radiation functions corresponding to lambda 1 t and lambda 1 2. Lambda 1 t and lambda 2 t. These functions are determined from table 11.2 and lambda 1 t equals to 2400 micrometer Kelvin and lambda 2 equals to 5600 micrometer K, and radiation functions equals to 0.140256 and second radiation functions equals to 0.701046. Note that radiation function at 0 to lambda 1 equals to radiation function lambda 1 minus radiation function 0 equals to radiation function lambda 1. Since radiation function at 0 equals to 0 and radiation function lambda 2 approaching infinity equals to radiation function infinity minus radiation function lambda 2 equals to 1 minus radiation function lambda 2. Since radiation function at infinity equals to 1, substituting into the emissivity equals to 0.5 to 1. That is, the surface will emit as much radiation energy at 800 Kelvin as a gray surface having a constant emissivity of equals to 0.5 to 1. The emissive power of the surface is equals to 12,100 watt per meter square. We have to bear in mind that the surface emits 12.1 kilojoule of radiation energy per second per meter square area of the surface. Now, for the view factor. Radiation heat transfer between surfaces depends on the orientation of the surfaces relative to each other as well as their radiation properties and temperatures. The view factor from a surface I to a surface J is denoted as by F I to J, or just Fij, and is defined as the fraction of the radiation leaving surface I that strikes surface J directly. Radiation Analysis on an enclosure consisting of n surfaces requires the evaluation of n square view factors, and this evaluation process is probably the most time-consuming part of a radiation analysis. The reciprocity relation, or the reciprocity rule, it enables us to determine the counterpart of a view factor from a knowledge of the view factor itself and the areas of the two surfaces. The summation rule is the sum of the view factors from surface I of an enclosure to all the surfaces of the enclosure, including itself, must be equal to unity. The summation rule can be applied to each surface of an enclosure by varying I from 1 to n. Therefore, the summation rule applied to each of the n surfaces of an enclosure gives n relation for the determination of the view factors. So the reciprocity rule gives 1/2n times n minus 1 additional relations. Then the total number of view factors that need to be evaluated directly for an n surface enclosure becomes like this. The bottom equation at the most bottom. For the superposition rule, sometimes the view factor associated with a given geometry is not available in standard tables and charts. In such cases, it is desirable to express the given geometry as the sum or difference of some geometries with known view factors, and then to apply the superposition rule, which can be expressed as the view factor from a surface I to a surface J is equal to the sum of the view factor from surface I to the parts of surface J. For a symmetry rule, the determination of the view factors in a problem can be simplified further in the geometry involved processes some sort of symmetry. Therefore, it is good practice to check for the presence of any symmetry in a problem before attempting to determine the view factors directly. The presence of symmetry can be determined by inspection, keeping the definition of the view factor in mind. Identical surfaces, they are oriented in an identical manner with respect to another surface, will intercept identical amounts of radiation leaving that surface. Therefore, the symmetry rule can be expressed as two or more surfaces that possess symmetry about a third surface will have identical view factors from that surface. If the surface J and K are symmetric about the surface I, then Fi to J equals to Fi to K, then Fj to I equals to Fk to I. So far, we have considered the nature of radiation, the radiation properties of material, and the view factors, and we are now in a position to consider the rate of heat transfer between surfaces by radiation. We consider radiation exchange between black surface only for this section. Consider two black surfaces of arbitrary shape maintained at uniform temperature T1 and T2. as shown in the figure 13.18. Recognizing that radiation leaves black surface at a rate of emissive power equals to sigma T power of 4 per unit surface area, and that the view factor F1 to 2 represents the fraction of radiation leaving surface 1 that strikes surface 2. The net rate of radiation heat transfer from surface 1 to surface 2 can be expressed as equation 12.18. Applying the reciprocity relation A1 F1 to 2 equals to A2 F2 to 1 yields the equation 12.19, which is the desired relation. A negative value for Q dot 1 to 2 indicates that the net radiation heat transfer is from surface 2 to 1. The net radiation heat transfer from any surface I of this enclosure is determined by adding up the net radiation heat transfer from surface I to each of the surfaces of the enclosure as expressed in the equation 12.20. The net radiation heat transfer from surface I of surface area AI is denoted by Q dot I and is expressed as equation 12.23. Solving for the GI from equation 12.21 and substitute into equation 12.23 yields the equation of 12.24. In general, in the electrical analogy of Ohm's law, this equation can be arranged as in equation 12.25, where Ri equals to 1 minus emissivity over E times emissivity, which is it explained about the surface resistance to radiation. The quantity emissive power minus Ji corresponds to a potential difference, and the net rate of radiation heat transfer corresponds to current in the electrical analogy. Can be illustrated as the figure above. That's all from me. Thank you.